In section 6.6, you have some problems that involve the work on a spring. So let's look at one of those. We know, ignoring the question for a second, that work is the integral of force. And we know that on a spring, the force is equal to K times X, where this is a spring constant. This changes for every spring. Or it's different for every spring. Each spring has one. So when we read our problem, it says if it takes 2 joules of work, so they're giving us the work, to stretch a spring from its natural length of 30 centimeters, so you can imagine that this is its natural at 30 centimeters, to a length of 50 centimeters, how much work is necessary to stretch it from 35 to 45? So the first clue they gave us was 2 joules of work to stretch from 30 to 50 centimeters. We have this equation that tells us about work, and we know that for a spring, this is the equation for force. So we're given 2 equals the integral of K times X dx. The work was 2. It said that was to stretch it from 30 centimeters to a length of 50 centimeters. Now what's important to remember is that the bounds are measured in meters, because we're going to get newtons, which has to do with meters. So the units force us to use meters for most of what we're doing here. The second thing to notice is that at rest, or natural length, we consider 0 meters. So even though it says from its natural length of 30, we're not integrating from 30, we're integrating from 0. And we're curious, how far do we take that away? 50 minus 30 is 20 centimeters, which is 0.2 meters. So we're integrating from 0 to 0.2. Now, they didn't give us the spring constant, so we don't know that, and we're still integrating kx. So let's go ahead and integrate. On the right side, whatever k is, we're going to get 2 equals 1/2 k times x squared from 0. I'm going to change my 0.2 to a 1/5, because fractions are a lot easier on these for me personally. So we're just trying to solve this for k, and this is pretty easy to do. Multiply both sides by 2 to get 4 equals k times. Now I'm going to plug it in with a 1/5 and plug it in with a 0. So 1/5 squared minus 0 squared. So that's 1/5 squared is 1/25. 4 equals 1/25 times k. Multiply by 25 and you get 100 equals k. So now that we have our k, we can now answer the second part of the question. How much work is necessary to stretch from 35 to 45? So we want to integrate the work is the integral from, if we're going from 35 to 45 and our natural length is 30, 35 is 5 centimeters away, which is 0.05 meters. And we're going to 0.15 meters away. And now we have our k, so it's a 100x dx. So we integrate. Work is 1/2 of 100, which is 50, x squared, from, again, I'll make it fractions, they're just easier, 1/20 to 3/20. So the work is 50 times, plug in the 3/20 and square it, minus the 1/20 and square it. 20 squared is 400, so the work is 50 times 9/400 minus 1/400. 9 minus 1 is 8, and 8 times 5 is 40, so 8 times 50 is 400. So the work is 400/400, which is 1 joule. Now that will really not happen very often, but I wanted to pick nice numbers, so the work is 1 joule for this problem. And that's how we do the spring problems. Sometimes they'll give you the k, and you just jump straight to the second part down here, because you already have the k, so you just want to integrate it. But always remember these 2 important facts. The bounds have to be in meters, so you change them from centimeters to meters, and at rest is 0. The biggest mistakes we see are people treating this as the integral from 30 to 50, or the integral from 0.3 to 0.5. They remembered to make it in meters, but they forgot that 30 was the natural length, so it's a 0. So, I hope that helps, and I'll see you later.